In this video, we'll be looking at the remainder theorem, which is useful for factorising polynomials, and we'll do an example of how you can do that. However, before I go through what the actual theorem is, I'm going to go through, if you remember in the video before about the division of polynomials, I use this example. And if you haven't watched it, that's fine. Just know that when this polynomial is divided by this, we get this answer, which is the quotient. You have a remainder there, and you have the divisor on the bottom. Now, there's for an observation, if we let px, which is the polynomial, equal x to the 5 minus 3x3 plus 4x plus 3, and then we say the p negative 3. So p negative 3, we'll let the divisor equal 0, therefore x is equal to negative 3. And what this answer is going to equal negative 171. Now you can sub that in, you can find that it actually does equal negative 171. And you'll see that this correlates to the answer. And this is equal to the remainder. And it's not just by chance. This is actually for when you're dividing all these polynomials and relates to what we're going to call the remainder theorem. So that's that. If you're dividing by a polynomial and you let that polynomial equal 0, whatever x value it is, and you go p that x value, you're going to get the remainder. So in a general sense, we can say that when px is divided by x minus a, the remainder is pa. So another way of thinking about that is pa is equal to the remainder. So therefore, pa is equal to the remainder, and then whatever the x minus a is. So a can be any type of constant. However, you can also divide by ax plus b, and then you'll slightly get a different remainder, which is just p negative b on a. Easy way to remember this is that you let the divisor, so x minus a, equal 0. So x minus a is equal to 0, therefore x is equal to a. Ax plus b is equal to 0, therefore x is equal to negative b on a. And you can see that that's just there. So the important rule, or not the rule, but the important observation from this is that if pa is equal to 0, therefore the remainder is equal to 0, then x minus a is a factor of px. And it's a factor because if there's no remainder, then that polynomial can be divided by the other polynomial. Then you'll just get a quotient, i.e. another polynomial. So you'd have px over x minus a will just give you another polynomial, sort of x4 plus 3x squared minus 2x, for example. And then this can also be applied for the other case. So if p negative b on a is equal to 0, then obviously the remainder is equal to 0, so ax plus b is a factor. And this is very useful. So to graphically try and represent what I explain this theorem, if we have y equals x minus 3 brackets x minus 1 equals x squared minus 4x plus 3, we can graph this by finding the x-intercepts and then graphing it. We get x is equal to 1 and x is equal to 3. Then we graph and we get a quadratic. And the reason why we have these intercepts is if we have y equals x minus 3 times x minus 1. If one of these is 0, then y is going to be equal to 0. Because y is equal to 0 times any number, so 2, 3, 4, doesn't matter what number it is, will always equal 0. So therefore, y will equal 0 if x minus 3 is equal to 0, or x minus 1 is equal to 0. So if we can represent a polynomial, a generic polynomial px, with regards to these factors, so let's say these three factors, whatever they are, in here, and we'll call one of them x plus a. Therefore, if x equals negative a, then that bracket is going to equal 0. So that means px will equal 0. And no matter what these other two terms are, because 0 times whatever they are will just equal 0. So that's sort of what the remainder theorem can show us. That if px is equal to 0, then that means one of these bracket terms is going to be x plus a, where whatever the value is you put in here. So let's say like negative a or whatever it is in there. And if it's one of these sort of bracket terms, then it's going to be a factor, because a factor is just something can be divided by, and obviously if px is equal to these groups of factors times by each other, then each one of these will be a factor by itself. So how is this actually useful? Well, we've got a question, factorize x to the 3 minus 3x squared minus 6x plus 8. Then we can use the factor theorem to help us factorize this. Now, it's very hard to initially see that this is equal to x minus 4, x plus 2, x minus 1. So we can't just automatically see that sort of answer. We can't use the quadratic formula as well, as it's x to the 3. So it's to the power of 3, not to the power of 2. But we can start off by saying that we'll say let px equal to the x3 minus 3x squared minus 6x plus 8. Then we can sub in some values. So let's say p0. Now this is equal to 8, which is not equal to 0. So therefore, x plus 0 is not a factor. And then we can sub in some other values. So p to the negative 1, which is equal to negative 1 to the 3, minus 3 negative 1 squared, minus 6 negative 1 plus 8. And that's equal to negative 1 plus 3 plus 14, which is obviously not going to be equal to 0. So therefore, x plus 1 is not a factor. Not a factor. Then we can sub in, let's say, p to the 1. P to the 1 is equal to 1 minus 3 minus 6 plus 8. So that's 9 minus 9, which is equal to 0. So now we can see that the remainder is equal to 0. Therefore, x plus 1, but rather x minus 1, because when it's whatever value inside that makes the brackets equals 0. So x minus 1 is a factor. So of x to the 3 minus 3x squared minus 6x plus 8. So we know straight away that one is a factor. Now we could keep on going through all the other values and find two other values which give us two other factors. However, that is going to take a long time. But we found one. So we know that x minus 1 is a factor. And from then, we can use long division. So we can say that x minus 1 x to the 3 minus 3x squared minus 6x plus 8. Then we can solve this. So we get x squared minus x cubed minus x squared. That goes down and gives us plus x squared, so minus 2x squared minus 2x minus 6x, bringing that value down. Times in that across and we get minus 2x squared minus 2x. So these always cancel, and if they don't, then you've done something wrong. Minus minus gives us positive 2 minus 6x, so that's going to give us minus 4x. So minus 4x going up to the top. Now I've actually made a mistake here, so numerical mistake I just realized. So if you're going through this, try and see where the mistake is. So the mistake was I put a negative there when it should have been a positive, so if you notice that could work. And so it was negative 2x, but then because it was negative 1 negative, that became a positive. So I'll get rid of this end bit. So that means I have now got negative 2x rather than positive 2x. So negative 6x minus 2x will give us negative 8x. Put negative 8 up here. Then bringing that plus 8 down, bringing that across, we get negative 8x plus 8. Plus negative 8x plus 8x is 0. plus 8 minus 8 is 0, so plus 0, 0 is just equal to 0. And then that always has to equal 0. So must equal 0. And the reason for this is because we're dividing by x minus 1, which we've already shown is a factor. That's because that is a factor. So we now have the quotient. That means we can write the factorize this in the factorized form. So x to the 3 minus 3x squared minus 6x plus 8 is equal to x minus 1 x squared minus 2x minus 8, which is equal to x minus 1 x minus 4 x plus 2. And that's just a simplified version of those two, are factorized. So we get this as the final answer. Now if you're confused about how we got the final, how it just equals x minus 1 and then whatever the quotient is, well I can just times them together. Because if we had px and we divided that by x minus 1 and the result was x minus 4 x plus 2, as there was no remainder. So it's just plus 0 over x minus 1, which is just 0. Then we can times x minus 1 from both sides. And px is equal to x minus 1, x minus 4, x plus 2.